Okay, we're going to look at some of the most basic definitions in algebra. We're going to look at relations, functions, domain, and range. And I'll try to keep this short because in all honesty, these are pretty simple concepts to understand. So the first definition we'll look at is what a relation is. So a relation, it is abstract, okay? So don't get me wrong when I say it's simple to understand. It's very basic, but it is abstract. So we'll try our best to get across the point. A relation describes relationships between inputs and outputs, okay? So very, very vague, right? So you have this group of inputs and you have this group of outputs, and you don't have to call them inputs and outputs. That's a common way to think of this because we might think of a relation as being a machine. You feed something in and you get something out. So one's the input, the other's the output. But the idea is, how do the inputs relate to the outputs? What's the connection between them? And we're gonna emphasize this concept using what's called a mapping. So that'll be the tool that I use to convey this concept. And so another thing to kind of keep track of here is when we talk about inputs and outputs, these two sets of items, usually they're numbers in algebra, but if we want to correlate this to a graph that has an x-axis and a y-axis, it can be very common to call the inputs x values and the outputs y values. So that's something you'll want to get used to, is inputs are x, outputs are y. And so let's look at an example of a relation. An example of a relation. And let's give it a name. Let's call this relation R, okay? So we'll sort of emphasize that here. Capital R is our relation. And we're gonna emphasize this relation using a mapping. And so the mapping on the left side is gonna be a column of numbers. Let's say we have 5, 2, and 3. And then we have another column of numbers over here. Let's just say it's 0 and 2, okay? And so these guys here, we'll say are our inputs. And these guys over here will be our outputs, okay? So this relation R, we're calling it a name, right? This relation R should define how these inputs connect to those outputs. How are they connected? And so just as an example, let's say that the input of 5 points at 0 and it points at 2. So in other words, we could say the input of 5 has an output of 0 and also an output of 2, just to give you the idea here. The arrows can indicate that 5 is the input and 0 and the 2 are the outputs. So we wouldn't necessarily have to label inputs and outputs like this because the arrows would tell us that story. Now let's say that 2, the input of 2, also outputs 0 and 2. And then let's say that 3 outputs 0, okay? So this relation defines relationships between these inputs and these outputs. And this picture is very visual, obviously, but this is called a mapping. Okay? So that's one way to represent relations with a very specific picture of the relationships, okay? Now, let's look at a couple other definitions. Let's look at domain and range. So what is domain? Domain is the set of inputs that have outputs. And so, for example, in relation R, the number 1 does not have an output. So the number 1 is not in our domain. So in particular, the domain of this relation R, the domain of the relation R is the set. So whenever we have a set of a finite number of numbers, we can actually make a list. And so when we say set, we use braces to indicate a set. That's very important. Too many students don't recognize the importance of this, and they'll use like a square bracket or a parenthesis, but we need braces whenever we're looking at a set of a finite number of values. So the domain of R is a set of inputs 5, 2, and 3. So we simply make a list of those numbers in no particular order, separated by commas, enclosed within braces. So this is the set of the numbers 5, 2, and 3. Notice none of the numbers are duplicated. You wouldn't list 5 twice, for example, because it's already in there. And there's no order to these. It's just a collection of inputs. All right. Now the range, what do you think the range is? I bet you could guess. What is the range of a relation? The range of a relation is the set of outputs. The set of outputs, okay? So domain, inputs, range, outputs. Domain, inputs, and x values, range, outputs, and y values, okay? So the range of this relation R is the set of outputs, which again is a finite list, not an infinite number of values. It's a finite list, 0 and 2. So we just make a comma-separated list enclosed within braces. So now we understand domain and range. Now, let's move on to what a function is. A function is a special type of relation, okay? So what is the significance of a function? Now, you'll see, we'll write the definition of a function, but just to motivate the idea, if you think about using a calculator, you hit a bunch of buttons, right? You type in this calculation of some sort, and then the final thing you do is you hit equals, okay? Or enter, whatever your calculator has on it. And when you do that, what do you expect your calculator to do? What would you like it to do? You want it to give you the answer, right? The one answer, the one output for your input. All right, so that's what a function is. It's not a calculator, that's a metaphor, but what is a function? A function is a relation. It's a relation, so it's still a relationship between inputs and outputs, but it's a relation where each input has exactly one output, okay? So in other words, you can't have any inputs with more than one output. That may be something you want to write down if you're taking notes. You can't have more than one output. You can only have one output. One answer when you give it something, right? Okay, so let's practice the concept of relation, function, domain, and range now. So let's consider the mapping F. Consider F. And this mapping looks like this. The inputs are the square root of 3, pi, -1/4, and 0.7 repeating. Now I know I'm being a bit obnoxious here with my choice of inputs, but what I'm trying to emphasize is your inputs could be, in algebra, you typically look at real number inputs. You don't have imaginary numbers, for example. So these are all real numbers. These can all be found on the number line. Okay, so they're perfectly fine as inputs. And let's say that the outputs are -5, 2 times the square root of 7, and 6, okay? And then the mapping looks like this. The relationships look like this. Square root of 3 outputs 6, pi outputs -5, -1/4 also outputs -5, and 0.7 repeating outputs 2 times the square root of 7. So the first question is, What do you think? Is that a function? Let's ask that first. Is it a function? And when you ask that question, in my opinion, you should always come back to this basic definition. Don't memorize some rule. A function, well, each input has one output. So the way to do this is you look at your inputs. How do I know these are the inputs? Well, they're pointing at the outputs. So these guys are my outputs, okay? So how do I determine if it's a function? Well, I analyze each input one by one. How many outputs does the square root of 3 have? Well, it only has one output, 6. Pi only has one output. -1/4 only has one output. And 0.7 repeating also only has one output, right? So all of the inputs have one output. So f is a function. This relation f is a function. All of those inputs have exactly one output, okay? Now let's see if we can determine the domain of this relation. Well, domain start associating with inputs. The inputs are these four meaning finite values. So we enclose them in braces and we simply make a list in no particular order separated by commas. So there is our domain for f. Finally, you can guess what we're going to do. We're going to look at the range, which is the set of outputs, -5, 2 square roots of 7, and 6, okay? So here's a function. It's a mapping. We represented with a mapping, and we were able to determine the domain and the range. Let's look at one other way to represent a relation, okay? And practice the same concepts. All right, so this next representation is called a set of ordered pairs. You can write that down if you think you'll forget. It's a set of ordered pairs. So let's consider this relation. Let's call it G. And let's say that G is this set. See that brace again, meaning set. So I'm going to have a finite list here. So G is the set of ordered pairs. So the first ordered pair is 1, 3. It's an ordered pair, meaning x and y coordinates. So that's the first item in our list, in our set. 1, 3, then we have 2, 4, then we have 5, 3, then we have 1, 4, okay? And so this set of ordered pairs is a relation. It relates inputs to outputs. Well, how does it do that? Well, ordered pairs are x and y values again. So to interpret an ordered pair as input-output, well, this is saying that the input of 1 has an output of 3. The input of 2 has an output of 4, etc. Okay, you could even draw this as a mapping if you wanted to, with all your inputs in a column pointing to all the outputs in a column. Now, first question, is G a function? Does each input have exactly one output? That's the definition you should always come back to. Don't memorize some other rule, in my opinion. So we look at the input of 1. How many outputs does 1 have? Well, in this relationship here, 1 has the output of 3. But down here, the same input of 1 has a different output of 4. This is not a function. G is not a function. And why not? Well, let's be specific. G is not a function because the input of 1 has more than one output, okay? Now, if we look at this further, you might be thinking of shortcuts. Don't do that. Think about the definition, because shortcuts will get you in trouble unless you've got a lot of practice. The key to shortcuts is getting a lot of practice in first so that they make sense to you later, okay? So a lot of people will look at this and say, no, it's not a function because 4 is listed twice. Well, what does that mean? That doesn't tell us anything about whether it's a function, right? A function says each input has one output. So if we look at this, the input of 2 has an output of 4, and the input of 1 has an output of 4. That's totally fine. Right? 2 has one output. That's fine. Has nothing to do with it being 4 showing up twice. The reason this isn't a function is because the input of 1 does not have one output, it has two outputs, okay? So G is not a function. Now what's the domain? Well, domain is the set of inputs, the set of X values, okay? So what are all the X values in this set of ordered pairs? Well, 1 is an X value. So I just list 1 as one of my inputs, comma. My next input is 2. Again, these don't have to be in any order necessarily. So 1 and 2 are inputs. 5 is an input. And then we have 1 again, but I've already got 1 in my set. I don't need to list it twice. So there's my domain. Make a note to yourself if you want to remember that you don't ever list duplicates when you make a set of finite values. All right? Then our range, you could probably figure that out on your own now, are the set of outputs, which are 3 and 4. And that's it. They're both listed twice up here, but we don't list them twice in our range as a set of finite values. So that's the foundation for function algebra. Those are all the basic definitions. Now we'll do some other examples. In fact, you know what? Let's go ahead and do something with a graph now. So we've represented relations with mappings and sets of ordered pairs. There are other ways to do it too. And one of those ways is with a graph. I'll have another video dealing with graphs and lots of graphing in algebra, of course. But let's consider this last relation. Let's consider this last relation H. And so this relation is a graph. Okay, so there's our plane, and we're not going to make this terribly precise here, not terribly precise, but let's say here's the x value of 1, and somewhere up here, doesn't matter where, we have an open circle. Now what does an open circle mean on a graph? It means that it's some kind of boundary point that's not included on your graph. It's a stopping point, but that point itself is not part of the graph. So, and then as we go to the left, let's say it's a straight line that slants downward. And then below 1, we're going to have a vertex of like a sideways parabola. So on the left side, we're going to have maybe something that looks like this, okay? And so here what we can see is we have arrows in lots of places. The arrows mean that the graph continues this behavior forever, okay? So that's important as well. So we have a boundary point for this line, and the boundary point is not part of our graph. So the question maybe is, is this relation H, is it a function? Does every input have exactly one output? Does every X have exactly one Y? And so what we do, remember this is our X-axis, we scan our inputs. We run across the X-axis and we find outputs, how many there are. So for example, if I look at this input, I don't care what it is, right? I'm not being terribly precise here, but if I look at this input and I scan the graph, I can see that this input only intersects the graph at one spot right here, which has this Y value, right? This is our Y axis. So this is our input axis, this is our output axis. So this input, this negative X value, this negative input has this output, which is a negative Y value. But the key is it only has one of them. So this input has one output, we can see that. And so if we scan, right, we don't have to do this a million times, but if we scan the X-axis, we can see that all of these X values over here, this guy here even included, for example, has one output, and we keep scanning, and these inputs all have one output. They all intersect the graph one time. And then what about when we get to the X value or the input of 1? When we get here, we can see that we have a point on our graph here, which means we have this output. So 1 definitely has an output. It's right there. It's that Y value. But then what about the open circle? When we look at 1, this point's not on the graph, so that does not give us another output at 1. So the input of 1 has exactly one output. We're good so far. The problem occurs when we scan after 1. Immediately after 1, we can see, like right here at this input, we have two different outputs, two different Y values. And you can see that that's true everywhere past 1. There are lots of inputs that have more than one output. So H is not a function. H is not a function. Many inputs And we could even specify the inputs bigger than 1. Many inputs have more than 1 output, okay? Many inputs do. Now, this occurs so frequently where you're looking at a graph and trying to decide if it's a function that there is a common shortcut. Again, practice with the definition. Every input has 1 output. Practice with that first. Get a good handle on that. And then you can use something called the vertical line test, which is very specialized. It tells you if a graph is a function. So the vertical line test says if there's a vertical line, such as right here, if there's a vertical line that intersects your graph more than once, it's not a function. That's it. We already know that. That's what the definition tells us. But it's kind of a visual shortcut, right? If I draw a vertical line right there, I can see that it hits my graph more than once. This is not a function, okay? I only need for it to happen 1 time. In this case, it happens many times. All right, now we're done. That's relations, functions, domain, and range, the foundation of functional algebra. Hope this is a good start for you. Go practice with it. Good luck.